Yeah, there was one new thing from last time, right? I mean, new as in you can, yeah, we'll prove this result. The column length decrease. You can use it for free. And it's not a book. I mean, in a way it is, because the way we put the cycles are in decreasing order. So it was like, but I don't think people understood it. Well, what's your program, by the way? In middle, yeah. Wow. There's a place where machine learning changes our understanding of the world. Is there a data course for astronomy? Like just for astronomy? I did a project in astronomy. Like, you know this work study program? You know John Percy? Okay. But is there any data course in astronomy? As part of the course? Like, is there like a experiment, like detecting galaxies and you have all the like tables and right. But that's the thing about astronomy, you have like billions of data, right? Okay, trillions. Huh? No, no, but you move around. What are you talking about? No, 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 that's not what I'm talking about. I'm saying like, let's say you want to make a statement about neutron stars. There's probably like millions of neutron, and then you collect the data of them. Yeah. But I'm just saying like, that's a beautiful, because data analysis thrives with data, right? Yeah, because you have the dimension reduction problem. Oh, right. I mean, it's a known fact, right? That if you want to change your network, you want to, like with cars, you can't possibly write down, you know, like I don't know. You will see this. I mean, I don't know. You guys, okay. Uh, yeah, like that's the whole point of machine learning. Not different. We don't. Machine learning is different. Machine learning is just classification, right? Right. Yeah. So I don't know. Did you see the game of AlphaGo? Did you guys see the match of with what was his name? Saying what was his name? What's this one? Hi, Sakura. Let's start. So we'll review today, except the first one will be a result. Yeah, so let me start from this sentence. So consider an important map of degree L, and these two are quantities. The dimension of the kernel for its higher power, and the dimension of the image of higher power. And we're going to prove the following fact. First, that this difference to consecutive is equal to the reverse for the images. You see how it flips? It goes from I to I plus 1. And I mean, we can prove this. I'm not expecting it. But the reason this is interesting is because this quantity here gives you the number of boxes in the ith column. So, and we're going to prove that it decreases. Okay, so when you go to the next column, you will have fewer boxes. Okay, that's what we're going to prove. So you can use it for free. How should you use it? I think the most formal way would be for you to write down in class. We showed that kernel of ni plus 1, kernel of ni decreases. Okay, from class. All right. Like you know, you will have some. You might have some young tableau or whatever, and you in your proof, because it's a proof question with tableaus. So then you will have to like, if you want to use this map, just say this. Like the columns decrease, the column lengths, which is the same as this. All right? That's what I'm saying. That's why I'm spending like the next 10 minutes. All right, question? Let's start. So first fact is this, that if you sum dimension and image, dimension and kernel, you get n. So why is that? Yeah. And so that's right away you get the first fact that this guy is equal to this guy is equal to the next guy, right? Because this is true for all I. And so you take the difference, right? So you bring this guy to the left and you bring this guy to the right. Good. So now let's show that it's decreasing, okay? So the trick is you look at this restricted map. So your Nilpotent map, but restricted at the image of NI. Okay, that's the trick. And we're gonna apply rank nullity to that. And that would be the end. So yeah. So if you apply rank nullity, you get that the dimension of the domain, right, is equal to image, so n of ni, which is this, and the kernel, right? I mean, usually you write kernel of n, but what you really mean is kernel of n intersect v, which is kernel of n. But here you restrict it, so you have to put intersection. Do you understand? Because you restricted your map, so you have to restrict your kernel. Okay, if you have a question, just tell me. So that's rank nullity. and you bring this guy to the left. So you have the difference of images, ni minus image of ni plus 1 is equal to this dimension, right? Now, can you tell me how does this compare with kernel of n intersect image of ni plus 1, which is the bi plus 1 minus bi plus 2? What should I put here? You say I should put this? Are you sure? Why is it the other way? You want to prove it? All right, let me prove it. So it goes like this, and the way you can memorize it is that eventually this guy becomes the zero now, which has zero dimension. Yeah, the more you apply it, you eventually kill it. But for consecutive ones, it's easy. So what is it saying? It says, so you basically kill off things. So we have V in the kernel of n intersect image of ni plus 1. And what do I want to show? I want to show that this guy is in the full thing, right? So you have two things here. You have some W like this, right? But this you can write it like this. Yeah. Yeah. Some W. So from here you get that V is an image of Ni, but you also have this. So you just intersect. Okay. Okay. Yeah. So yeah, that was it. So we have the right hand side decreases. So the images decrease. So this guy here decreases. So we prove that kernel of ni plus 1 minus kernel of ni is bigger than the next guy. Is that okay? That's what I just proved. Yeah, yes, because I proved it. Yeah, I mean for everything. Everywhere. All right, so let's go back to these questions we have from Tuesday. So let's use this fact to help us identify. So does this signature, so do like Caesar, yes or dead? Put the sword in. So does this, actually I think it was this and this. It wasn't like this. It was like kill him or don't do nothing, hold it. Yeah. Yeah, good. So is this nilpotent or no? Is it nilpotent? What do you guys think? Yes, no? Oh, okay, good. Parf, I can't see. Did you kill him? Sakura? Yes, all right. All right. Yes, and you only need that you have a valid tableau. So here kernel of n is 2. and kernel of n squared is 4, right? And you indeed have that kernel of n minus 0 is less than kernel of n squared. Yeah, which is true. I should put the numbers the other way. No. He's right. I mean, it should be. It's like this. It can be equal. Yeah. The way I wrote it right now. Yeah. No, I got mixed up. Right. So it has to. You have to decrease, but it already equal. I don't know. It doesn't matter. So now let's figure out. Now that we have the Nilpotent map, let's figure out all the other stuff, right? So, what's the tableau look like? No, you can, one of you can just tell me. I mean, astronomy. What does the tableau look like? Right now? Yeah, okay. First column. Right, yeah. Yeah, so just so because this guy has 2 elements, and then you added 2 more, and you have 4 in total. Okay, the dimension of the space. Yeah, let's also do the matrix since I want you to be comfortable. So can one of you tell me, someone else now? Can someone tell me what the matrix will be? What's the Jordan canonical form? No, just tell me what how does the matrix look like? Sure, yeah. How many? So you okay? Let me follow what you said, and then we'll talk. So I put a 1, okay? Sure. All right, let me see. So you're saying it would be something like this. Let's see. So how do you figure this out? There's many ways. Let me go one at a time. First, you can do it by cycles. So you go row by row. Okay, so that's one way. You stare at your tableau and you're like one element, another element. So I'm gonna have a 2 by 2 block and another one. So 2 by 2, like you said, and you get your two guys like this. Is there another way? How else would you do it? I mean, unless you have a concrete matrix where you have algebraic multiplicity and yeah. So just from the table, just go by the number of elements in each row. That's all. I can't think of that. If you have something else in mind, you can tell me. I mean, how did you figure it out? What? Yeah. No, you cannot move the one at all. You cannot touch the one. This is the only place one can go. You only have upper triangle, not lower triangle. So, no, talk to me. Are you saying you want to have this? What is 3? You mean put it here? Here? No, you cannot. Because that's not the Jordan block. Like this guy is not a Jordan block. It's not. The first column must always be 0 because you kill. Yeah, you kill it. It's the 0 element. All right. No, good. These are good questions. It's good to clear them out now. Then later. Okay. What about 1 to 4? Why not? I need a proof. Now you have results. Which one? Perfect. So you have kernel of n. Which one do you want to do? No, because they both fail. But so you have kernel of even the kernel of n. So this guy is 1, which is strictly less than kernel of n cubed minus. I should write the number 2. Kernel of n squared. But this is also bigger than kernel of n. So they both fail.
Oh, like, well, because it fails, like, this is bigger than the second one.
Sure, but I'm just saying, it fails the both. So now let's find, okay, yeah, so it's not table. What about this guy? Someone else. Thank you. Art? Okay, so let's see, you have kernel of n what? No, kernel of n what? Okay, so which one are you looking at? Kernel of, okay. This is equal to what? Uh-huh. Okay, what about kernel of n minus 0? Uh-huh. No, mine actually, did I make a mistake? So this guy is 1. Oh, yeah, okay, right. So this fails, right? Yeah, thank you. So you have, yeah, kernel of n. Yeah, this was in your homework, so this was, and okay, good. All right, perfect. So you can use this guy. Now, what about this? Sakura, what do you think? What do you guys think? Does this have a valid tableau? Huh? Oh, okay, we killed it. Sakura, what do you think? I don't think it's valid because it increases. Right. So very quickly we have 3, 2, and then this guy is 3. So you have this. What about this guy? How did you find this? Is it? So it's 3, 2. What are you talking about? Right? So yeah, we'll do it right now. So okay, you have it. Yeah, can you give me the tableau? And okay, someone else. Parth, can you give me the matrix? Like one block at a time. Let's not. What's the first block? Yeah. So okay, how many entries do I have in the first? Let's go column by column. Perfect. Very sure. So remember how we did this, right? Do you know why though? Are you sure? Because the first entry was the last one, and then you have n minus 1 b. So then when you act on this, you get this. Is that okay? Yeah. Don't try to memorize, try to understand. Okay, what about the next one? I'm talking to Park. Thank you, Ismail. Yes. And then, okay, that's the first block. So how big is the first block? 4. So, yeah, so it should be 4 by, did I miss a, so it's not big enough. What? No, no, I'm asking him. Is that what you said? Yeah, yeah, exactly. Okay. So, yeah, so this is the first block. And yeah, what's the second? How big is it? Yeah, yeah, exactly. That's all. So this, and then last guy. Yeah, just a 0. Perfect. Yeah. Yeah, for nilpotent. If you have a general map, it will be the eigenvalues. We'll do an example. Hopefully, we have some time. Yeah, we'll talk about this. I mean, you should know. But I mean, a general map is one that's not nilpotent. It doesn't have to be nilpotent. No, 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 no. Wait. So general linear map is just any linear map. Doesn't have to be nilpotent, right? So the kernel, it could be injected. It could be. Oh yeah, yeah. A minus lambda I. Right, right, right. Okay. Okay. All right. So we find this guy. How many more should I do? Shall I do this? Yeah, let's keep doing because this is good practice. So is it? Oh, some people say no. Some people say no. You think so? Let's see. So we have 3, 3 and 2. Yeah. So who else? Yeah. What's your first name? Huh? Jimmy. Can we do the tableau? Please? And can you give me the first block? Uh-huh. Yeah, yeah. And second block? Perfect. Yeah. And third? Good. Sorry. Disconnect. Oh my, is there more? Okay. All right. I don't know how far, like, I have more examples, so we'll see. Just a rough overview. So make sure you know the definitions, okay? We might ask you for some of them, like we will ask you for some of them. So make sure you know the definitions of them and how to get them, like the theorem, okay? These were the key examples. Make sure you understand these continuous functions, all that stuff. So proving a set is a subspace. How would you do it? Can you give me 2 ways? Yeah, sure. Right? That's one way. Call it W. And then what's the other way? No, no, no. I mean, I'm saying like it doesn't always have to work. But what's a way we've been showing? Yeah, yeah, yeah. So if W is equal to kernel of T, or W is the image of T, or something. I bet this goes 1 to 1. I bet there's a way. There's probably some countries. that you can have it always. That if it's a subspace, then it's the kernel of some T or image of some T. Oh, you're right. So you can use just the basis. Okay, let me see. But then it will have to be zero everywhere else because you only want it to map V to W. No, like the projection map. What am I talking about? Projection map, right? Yeah, just a projection map. Huh? Oh no, like you give me any W. This guy is the image of projection of W. Yeah, yeah. So this guy always works. Yeah, but the point is, in order to have the projection, you need an orthonormal basis, and there's a lot of stuff here. But yeah, so I mean, it's kind of involved. Yeah, it'd be hard to. Okay, anyways, let's move on. A basis. So I have some points here. First, yeah, you use the definition, right? We even had a construction. So for every vector space, we had a basis. We built it, right? We built the basis. But let's see. Yeah, so my question is, suppose we give you W inside V, and you have a basis for V, for W, like W1, W2, and you want to extend to V. Let's say this dim V is 4-dimensional. Yeah, two. So how do you get a full basis? Yeah, but no, in practice though, like in practice they will ask you to find the right. Right. So you will have to solve. Uh, you have to solve x w1 equals to 0 and x w2 equals to 0, and x uh, you will get w perp. So from here you will get x1, x2 solutions, right? Is that okay? No, don't risk it. Yeah, it's better to show how you got your work. What? Yeah, this is in a. I mean, okay, I don't know why I wrote dotted because somebody said dot. It doesn't. Take orthogonal. How about computing dimensions? So one is the definition by a basis. How do you show that the dimension is different? Oh yeah, sure, yeah. Like for any, but let's say we give you a concrete space. How do you show that the space is empty? Yeah, well, that's what I'm saying. Like, what would you do? What would you have to give to show that, oh, it's infinite? Yeah, but like, what kind example of what? What will it be in the example? Yeah, whatever. I mean, we give you some space. What do you have to give to show that it's infinite? No, it's easier than that. Do you guys know? I mean, I know you know. It's just it's a language. Like, I mean, how do we? What is dimension? You guys you're overthinking it. All I'm asking is, just give an infinite li collection. That's all I'm saying. You understand? Yeah, it will be an right. Is that okay? Because we proved that dim v is bigger than or equal to the size of all Li subsets. So in this case, infinite. In this case. So, okay. And yeah, randomity, direct sum is also nice, but here we used yeah. So here I don't know. I mean, this is like a calculus question. Let's say you want to find W perp, right? And you can like solve this equation, right? N minus stuff like that. All right. What else? M2 material. Again, make sure you know all of these definitions and theorems. Just to be clear, because it did show up on Piazza, so I want to find here. So diagonalizable. So let's do a short review together. So when is a matrix diagonalizable? No. No, I want the definition. We had a definition. These are results. Okay. So the definition, I'm not saying the result. It was no, I asked what is diagonalizable. The eigenvectors of T form a basis for B. Okay, this is diagonalizable. What about orthogonally diagonalizable? No, you already talked. Jimmy? So, I mean, or orthonormal, but yeah. So there exists orthonormal eigenbasis for V. Okay. But V in our course, I know this is very confusing because it's not necessarily true out there. V is real in a product space. Okay. Huh? Well, no, when we're talking about orthonormal, orthogonally diagonalizable, we're talking about a real inner product space. That means that, going back to what you said, call this basis beta, then you have TB is equal to P diagonal and then P transpose, and they have real entries. Okay, and P inverse equals P transpose. That's orthogonality. Okay, and then I don't want to clean this up. So you have one more. So let's make sure we are on the same page. Unitarily diagonalizable. So what's the definition of this? Go ahead, Paul. Yeah. Okay. So stay with me. Yeah. And then eigenbasis for V, and then call it B. And then what can you say about TB? Yeah. So P, D, P star, and they can have complex entries. And you have that P inverse is equal to P star, okay? That's called being unitary. What? Yeah, it could not, but it could. Every real, I mean, yeah, every real number is complex. Yeah, but anyways, that's where the names come from. And in this course, we make a distinction for real and complex. And this is not necessarily true out there because you could have P transpose equal P, and you could be complex, like one I, one. Or like, no, what did I want to say? No, I had an example, I don't remember. But P transpose, let's see, I need an invertible matrix. Put I here and 0, like this, okay? This guy is invertible, and take this to be P inverse, so that you have the, no, what am I talking about? No, it was the rotation matrix. Let me, I forget, sorry. But there are matrices that have complex entries, and I think I have an example next, that they equal to the inverse. So, but in this course, we made this thing that when you hear orthogonally diagonalizable, just think of real. Unitary, think complex. Don't mix them. All right. Sakura, is that okay? All right, what else? Yeah, for key examples, were dot product, this matrix inner product, right? Where A from your homework, remember? So yeah, make sure you review this stuff, right? So emission dot product, coincident product, altitude product, and again, the guy from your homework. So make sure you learn the stuff from your homework. Let's go over some counter examples. Diagonalizable, but not normal or unitary. So what was the spectrum theorem? Normal if and only if what? So what should I write? Diet what? Yeah, unitary. And self-adjoint for in the real case. If and only if what? Yeah. Okay. So here you have diagonalizable. So there is a basis, but it's not an orthonormal basis. Okay. As you can see, these two vectors are they're not orthogonal with respect to the. I mean, I can do it. So you have -1 times 1 and 1 times 2, which is 1. So it's not 0. Yeah. I mean, no, you cannot assume it. But in this case, I mean, in this very specific example, you have a matrix, a linear map over R2, and the natural inner product is the dot product. No, but the way you should argue it is actually even normal. What do you mean normal unless you have a linear product? So yeah, here we mean dot product. Yes. Okay. Another example is you have a matrix that's unitary diagonalizable or normal, but it's not orthogonally diagonalizable self-adjoint. So can you tell me why it's not self-adjoint? So this is a result. I don't expect you to compute this. There's a result that immediately proves you that this guy is not self-adjoint. We prove the result about self-adjoint maps. Who said that? Yes. What? Yes. I mean, no. I mean, it's harder than this, isn't it? Like it's not every representation. We're talking about, huh? No, like self-adjoint has to satisfy, you first one has to specify an inner product, right? Um, and so, anyways, my question is easy. So, yeah, it doesn't have to be simple. This is like, but okay, this is easier than what do we know about self-adjoint maps? I guess, yeah, okay, fine. So you can do it that way. The thing I wanted to hear is that you have complex eigenvalues and self-adjoint maps have only real. Um, but this example is interesting because it's normal. Yeah, it's the rotation matrix, and it's also orthogonal. So 0 minus 1, 1, 0 times its inverse, which I remember it was like. So what is it? You have like this, and it was the other way. So it was like this, and you get 1, 0, 0, 1. Okay, so this is P inverse or M inverse. This is M. Okay. This is the pi 4, wasn't it? No, pi over q. Yeah. So this guy takes you 90 degrees. So it's orthogonal. Why is it orthogonal? Because do you observe something about M inverse? How does it relate to M? Yeah, but what's the relation? M inverse is equal to what? Yeah, and that's the definition of orthogonality. That your transpose, your inverse is equal to the transpose. Good. That's right. That's right. That's right. That's right. And then, yeah, because I also heard that. So you can have a matrix with distinct eigenvalues, but the eigenvectors can be not orthogonal. So you can do this. You can compute it, and these are the eigenvectors, and they are not orthogonal. They are linearly independent, but they're not orthogonal. So you have orthogonal implies Li, but not conversely. Okay, so they don't go both ways, and this is the context. Understand? All right. Yeah, but what if you have permission and distinct eigenvalues? What result do you know? Huh? No, this is for Nilpotent. What? Oh, I heard 0. I'm sorry. I'm sorry. I was like, what? Uh, um, anyways, I mean, yeah, this is not hard. Yeah. So we proved that distinct eigenvalues for Hermitian implies orthogonal. I see. So let's say you want to compute change of basis. How would you do that? So first you have the definition. So TB is equal, the first guy is TB1, right? TB2, and you write it in terms of the other BIs. A one, column one, AI one. Okay. Right. So that's the definition. Is that okay? And usually that's the fastest. Anyhow. Then you have one with projections. All right. So this AI ones, it's up to you. So we have, if you have if B is orthogonal, then the AI one is given by the projection of TB1 to BI divided by the norm of BI. Right? Is that okay, Jim? It will be the so A11 to AN1. I'm just saying there's two ways to find this coefficient. Either you just write it in terms of the BIs, which could be a nightmare because the BIs could be very complicated, or you find them one by computing the projection. But you have to know that they're orthogonal. Otherwise, this doesn't work. What?
Like this formula.
This formula only works if the BIs are orthogonal. Then it doesn't work. No, you have to do it by hand. And what was the matrix representation for T star? Yeah, so it will be so they commute. Yeah. Projection, yeah. So make sure you don't make this mistake in the definition of projection of W of U. You have to put it first. Otherwise, we talked about this before. Otherwise you don't have linearity. You have conjugate linearity, but you want your guy to be linear, so you have a subspace and all this stuff. Okay, what else? Yeah, when you want to find the basis, I think we talked about this. So let's say they ask you to find an orthonormal basis for some abstract object. I think the best way is you map your space into Rn, your subspace, so gamma b of W, and you find your basis, like whatever, and like V1 to Vn, and then you come back to your space by taking their inverses. Okay, and isomorphisms preserve orthogonality and basis and stuff. Yeah, we talked about eigenvalues. Again, same trick. If you want to find eigenvectors, but usually it will be for a matrix. So we haven't really tested on that. But that's the way to do it. You find it for the matrix and then you can come back. All right, what else? Yeah, so we talked about this guy. Make sure you know this key example for nilpotent. Right? So this was in your homework. Make sure you compute its degree. That indeed is nilpotent. Okay. And yeah, I mean, we did all that stuff today. You don't have to go on it. So you can read it on your own here. All right, okay. Good luck, all the best. It was good. No, they were good questions. There's no damn question. Yeah.